So we're looking at exponential functions, and these are quite topical at the moment. If you look over here, here is a graph that I made at the start of the coronavirus pandemic, and as you can see, you can model it using a bit of an exponential increase, and this is how the graphs are modeled to start with. Okay, so you'll find exponential functions in science with things like bacteria growth. In physics and chemistry, you might get exponential decay, so half-lives. And in maths, you will have seen this before when looking at things like compound interest. And sort of losing money over time. So depreciation. Okay, so you've seen this idea before, and what we're going to be focusing on is a function f of x which looks like this: a to the power of x. So you're quite happy with functions which are x to the power of something, x to the power of a. So you may have had x squared, so quadratic, or a cubic, x to the power of 3, perhaps even a quartic. Okay, but it's a to the power of x. Now, the way I'm going to do this is we're going to look at a few different values of a to start with. So we're going to look at 3 brackets. We're going to look at when a is greater than 1. We're going to look at when a is less than 1 but greater than 0. And we're finally going to look very briefly at what happens when a is less than 0. Okay, because this is a very interesting one. We're also going to look at what e is and what the graph of e to the x looks like. Okay, so over here I have the graph of f of x is 2 to the power of x. Remember, we are first going to look at what happens when our a value is greater than 1. So if I start at 1, hopefully you can see that I have a flat line here. That's because anything to the power of 1 equals 1. As I increase this a value, we notice the graph gets steeper and steeper and steeper. Okay, so for example here at 3, we're doing 3 to the power of 1, then 3 to the power of 2, 3 to the power of 3, etc., etc. So it's going up in powers of 3. Notice how it doesn't matter what value of a you have, it always goes through at 0. And this is because a to the power of 0, just like anything to the power of 0, equals 1. So every graph, so every exponential graph goes through 0, 1, as long as you haven't translated it. So I'm just going to put little star before transformations, because we can always move a graph. Okay, so that's what happens when a is greater than 1. It gets steeper, but it goes in a generally sort of this direction, okay, positive direction. It gets bigger and bigger and bigger. Okay, as you get less than 0, you get fractional powers. So you'll get, for example, a to the 1, a to the 0, and then you'll have a to the -1, a to the -2, and that's why our value gets smaller and smaller and smaller. Right, let's look at what happens when a is between 0 and 1. Okay, so for our function, f of x equals a to the x, when a sits below 1 but more than 0, let's see what happens. So we have our positive, kind of generally positive looking exponential graph when we're above 1. When we get to 1, we flatline. And at this point, you might be thinking it might go down here. But if we think about this really carefully, we're actually going to go the other way. So what we have is this downward slope. And this should make a little bit of sense. And I'll use 0.7 as an example. So going back onto here, if we have 0.7 to the power of 0, that gives us 1. 0.7 to the power of 1 gives me 0.7. 0.7 to the power of 2 is 0.49, etc., etc., etc. So as you can see, our value is decreasing. Because we have a number less than 0, if we raise it to a bigger power, the number gets smaller. Okay, so the further we go this way, the smaller it gets, to the point where I get a very, very small answer very quickly. Okay, so if you look here, let's go back to our 0.7 example. Again, we go through at 0, 1. We'll always do that. Anything to the power of 0 is 1. By 2, we're at 0.49. At 4, 0.24. 6, 0.118. And we get smaller and smaller and smaller until by the time we're at kind of 16th power, we're in the thousandths. Okay, so 0.003 something. Okay, so these graphs decay very quickly, but in their original state we'll go through 0, 1. Okay, so as that power gets bigger and bigger and bigger, the number gets smaller and smaller. Okay, if I plot two of these graphs, and I add a slider for B as well, what we can see is that these two graphs, they will both go through at 0, 1, and they'll just go in different directions, like that. Okay, so the black line in this case is when we are greater than 1, the purple line between 0 and 1. Okay, so the big question is what's going to happen when I go below 0? So if I have f of x equals a to the x, and I make s, and I make a less than 0, what's going to happen? Well, let's have a little think. Okay, let's try a number. So a number less than 0, let's go for -2. That seems quite nice. So we have f of x, and we're going to go -2 to the power of x. Okay, I'm just going to put that in a bracket to make it clear. So if we go through this, let's start with 0. Well, when it's 0, okay, so -2 to the power of 0 is 1. Anything to the power of 0 is 1. When I go -2 to the power of 1, that gives me -2. Okay, so I go 1 -2. -2 squared is +4. -2 cubed, -8. -2 to the power of 4 is +16. -2 to the power of 5 is -32. -2 to the power of 6, +64. Hopefully you can see what's happening here. We have positive, negative, positive, negative, positive, negative, positive, negative. Okay, well this doesn't seem necessarily like a bad thing until we sort of try and plot it and we actually put it in. So here we go. Here's our purple graph, and I'm going to go from positive to below 1 to below 0. Now we're not missing this graph. It doesn't exist. Now I want us to realize why this graph doesn't exist. If I plot these points that I've made here, I start at 0, and that gave me 1, so we'll plot a 1 on here. When x is 2, I had -2, so let's put that here. When I had 2, I got to 4, which is about here. X is 3, I had -8, which must be about here. 4, +16, which must be right up here. Power 6, I'm going to run out of space here, -64. Finally, 1 to 8 is right up here. Okay, so a bit of a weird looking graph. And what we can't do, we can't just do this. That doesn't make any sense. That's not a function. We also can't do what we want to do, which is draw an exponential graph. That'd be nice, but what about these points? Sure, we need one for them as well. That's a bit weird. What actually happens is it's impossible to draw this graph, and I want to kind of make sure you understand why it's impossible to draw this graph. Notice on my powers, when my power was odd, I got a negative answer. Okay, so these ones down here were odd powers. When I had an even power, that was up here. These were all even powers. Okay, they gave me an even answer. So you might think, okay, well, it's just going to go odd, even, odd, even, odd, even. So why can't I draw this graph? I'll tell you what, let's draw it. Let's say that is right. Okay, well, that's fine. But what if I zoom in here? Now, what's going to happen when my power isn't an integer? What about minus 2 to the power of, I don't know, 1.2? Well, minus 2 to the power of 1.2 gives me an even answer, whereas minus 2 to the power of 1.3 gives me an odd, because 2 is even and 3 is odd. I could sort of drill down even finer. I could say that minus 2 to the power of 1.21, well, that would be odd, because it finishes an odd number. Minus 2 to the power of 1.212, going to thousandths, that one would be even. So actually, the reason I cannot plot this graph is because it doesn't link up. There are an infinite number, just in here, there's an infinite number of odd and even powers. For example, I could have minus 2 to the power of 1.22222222222. That's an even point, whereas minus 2 to the power of 1.222222221 is odd. So that goes below the axis. So what I end up getting, if I was to try and join all these points, I would have a solid block like this. And even then I wouldn't have that. So essentially the reason your computer or your phone cannot plot this is because essentially it'll be plotting this big mass of points. When you zoom out though, essentially what it would look like, if we just had all the dots there, it would look like a nice exponential going this way and an exponential going this way at the same time. Bizarre, okay? It's not a function because there would be two lines. Now, this is all a bit kind of pie in the sky thinking. It's impossible to do it, okay? So all you need to remember is that when a is less than 0, you cannot get a graph, okay? And it's for this reason, odd and even powers. Now, you might be asked to plot something. Like f of x equals 2 to the power of x, and what you'll need to do is be able to sketch that, put some values in, and draw it out nicely. What you might also be asked to do is to draw the graph of 2 to the power of x plus 1. Now, what I'll tell you about this is that exponential graphs follow the same rules as any other transformation. Okay, so for example, in this case, the plus 1 is going to shift the graph up 1 in the y direction. Okay, another example. If I had, for example, 3 times 2 to the power of x, okay, that's going to stretch in the y direction. Another one, I could have 2 to the power of x plus 1. Well, that's going to shift the graph to the left. Shift 1 left in the x direction. And finally, you might get something like 2 to the power of 3x. Okay, well this compared to 2 to the x is going to be a squash in the x direction. Okay, so it follows all the same rules, transformations, Okay, and what I could do, I do this sometimes, I write a f of x, I write a f of bx plus c plus d, and if you can tell me what a, b, c and d do, then you can do these transformations. A, stretch and y, b, squash and x, c, translate in x, but it kind of goes in reverse, remember? And finally, d is translate y. That works the right way around. Okay, so exponentials follow the same rules as transformations as any other graph, so don't get freaked out by them. Draw the original graph, then move it. And if you need to, put some values in. A special case of exponential functions is when you have a graph called e to the x. Now, what I want you to think about with e to the x is that e isn't, well, it's special, but it's not special any more that it's just a constant. We've come across some constants in maths before. Pi is just a constant. It's just a number, okay? It's 3.14159 ... We've come across some other constants like the square root of 2, which is 1.414-ish. And, you know, we come across other constants like 1. 1's a constant. 1 is 1, by the way. Further maths, you may have come across I, square root of -1. And e is just another number. Okay, and if you type it into your calculator, you get e coming out to 2.71828 ... Okay, so these are all just constants. Okay, they're just mathematical constants that we know. So e doesn't do anything special, it's just a number. So basically the graph of e to the x comes between the graph of 2 to the x and the graph of 3 to the x. Okay, so if we look at it here, the graph is somewhere in here, okay? In fact, I'll plot it for you just to show you. E to the x, there it is, okay? So there's 2, there's 3, it's just shy of those two. Okay, so the graph of e to the x is just an exponential graph. However, e is pretty special. Okay, e is a very special number. And I'm going to show you why. So let's do a little thought experiment. Let's pretend I give you £1. And I tell you that I'm going to give you, I guess this amazing banking opportunity, I'm going to give you 100% interest. Okay, so 100% interest. Well, if I give you 100% interest, you would times your number by 1 plus 1. And I'm going to give you that for 1 year, okay? So to the power of 1. So this is 1 times 2. End of the year, you have £2, okay? Now you've got to be pretty happy with that, okay? You ain't going to find an interest rate as good as that anywhere. Okay, well, I'm going to improve the offer. I'm going to tell you that I have £1, but I'm going to give you interest. I'm going to give you half the interest. Ooh, doesn't sound so good, does it? But I'm going to pay it to you twice in the year, so every 6 months. So we're going to have them twice. So if we do this, get the calculator out, I'm going to do 1 times 1.5 squared, and you get £2.25. Okay, even better. That's great. Okay, moving on. What if I said to you, okay, I'm going to give you 1/12 of the interest. I'm going to give you 1/12. Okay, the interest I gave you before. But I'm going to give that to you every month. So 12 times a year. Okay, but then I'll do 1 times 1 plus a 12th. And I'm going to give you that once a month. Right, so that gives you, at the end of the year, £2.61. Even better. Okay, well, let's take this even further. Let's say your pound, I'm going to increase it by 365th of 100%, but I'm going to give you that every single day. Every day you're going to get that. So I'm going to do 1 times 1 plus 1 over 365 to the power of 365. This gives you £2.71. I'll add a few more details on here. £2.71 456. Okay, here we go. How many seconds are there in a year? I'll tell you what, let's go for minutes. How many minutes are in a year? 365 times 24 times by 60. Okay. So there are 525,600 minutes in a year. So I'm going to give you that fraction of the 100% interest. I'm going to give that to you every single minute. Let's see what happens. Let's see what I get. So 1 times 1 plus 1 over to the power of that. Okay, I get 2.71827. Let's go even more silly. Let's just do one more step. Every second. Okay, so 525,600 times by 60, so per second. So that's 1 and 1. I'm not going to read it. 31536,000 to the power of that same number. Essentially what I'm saying is every second you get that fraction of 100% interest. Okay, so 1 times 1 plus 1 over, and that gives you £2.71 828 1615. I'll put all the digits on. So we've tended towards this number. And remember that E is this number. Your calculator gives you E as 2.718281828. Okay, so we're out by 2816, 1, 2, 3. So the last 3. So we can get that accurate to 1, 2, 3, 4, 5, 6 decimal places. So essentially E is a number which is the amount you can get to if you have 100% interest. If you have instantaneous interest of 100%. That's one way of explaining E, and that's one place you can get it from. There's lots of other explanations, but that's the one that I quite like. So here's the graph of e to the x. Now, why is it so special? Well, the reason it's so special is that if I have f of x equals e to the x, and I differentiate it, if I differentiate e to the x, I get e to the x. So what this means is the gradient function of this graph is the same as the graph itself. That's pretty big. So when you differentiate it, this is the gradient function, and it's the same. Okay, it stays the same. If I integrate it, if I have the integral of e to the x dx, I get e to the x. Now what this means is, if I integrate it from this point, I get e to the x. I get the same value from that point. So when I integrate it or differentiate it, it stays the same. And I'm going to give you a few examples of differentiating e to the x. So here are 4 functions, exponential functions, including e, and we're going to differentiate them. So for the first one, if I differentiate this one, I differentiate e to the x, I get e to the x. If I differentiate x, I get 1. This next one, e to the 2x. Well, e to the 2x becomes e to the 2x, and then because I've got a function here, I differentiate that, which becomes 2, and I times it by 2. So 2e to the 2x. 2e to the x, well, this is going to stay the same, e to the x, and the 2 stays there. If I differentiate 1, that goes. Okay. Finally, 4e to the minus 2x. Again, I rewrite e to the minus 2x. I differentiate this, which becomes minus 2. I times it by 4, so this becomes minus 8e to the minus 2x. Okay, so I've given you a brief introduction into exponential graphs and an introduction to e. Have a go at differentiating, have a go at plotting those functions, and good luck.